In this session, we will solve a numerical problem based on the theory of rotating disk. The problem given here is that we have a disk which is of 750 millimeter outside diameter and 150 millimeter hole, that is the inside diameter, and it is shrunk fit around a solid shaft. And the radial shrink fit allowance is given as 0.075 millimeters. And the question asked is, at what RPM will shrink fit loosen up due to the rotation? Now, what it means is that when both this assembly of shaft and shrunk fit disc, they will start spinning, the shaft will expand by certain amount. So shaft expansion, radial expansion of the shaft. So you have the shaft and then surrounded by the disc. So there will be some radial expansion of the shaft, which I'm calling as URS. And we are now concentrating at the radius of interference, where the shaft outside diameter lies. So at this particular radius, let's say the expansion of shaft is given by URS. And at the same radius, if you use the hollow disk formula, you will get another displacement, which will be UR, that is the radial displacement of the disk. So that I'm calling as URD. Now, as long as both these displacements are equal, nothing will happen. The joint will never loosen up because the shaft and disc will always remain in shrink fit condition. But because the shaft is rigid, relatively rigid as compared to the disc, what will happen as the speed increases, the displacement of the disc will be more than displacement of the shaft. And when the difference between these two becomes equal to the interference, the radial interference which was initially made to happen, at that point the separation will happen. So this condition would be uh, equivalent to saying that the difference between radial displacement of the disk and radial displacement of shaft must be equal to the radial interference which is given in this particular formula. Now let's understand this particular situation physically, or let's look at this particular condition which I said the difference must be equal to radial interference in more detailed fashion, so we understand what it means. Let's consider a situation where the disk and shaft are not assembled, so the disk is having inner diameter which is radially shorter by a distance of delta than that of the shaft. So we will have to heat the disk. So now consider that we are heating the disk. So we have to heat it by some amount delta T, and that delta T amount would be given by the expression, that is whatever radial clearance that must be overcome. So you have to heat the disk such that its inner radius expands by an amount which is equal to delta, and that would be given by this particular formula. When this is the case, the disk, that is the blue portion, the inner radius would match with the shaft outside radius. Note that the shaft we are not heating, only the disk we are heating. And then you can insert the disk over that of the shaft. Now, after this, in order to cause the shrink fitting, you will cool down the shaft, the disk which you are heating. So once you cool down, you will get the assembly where both the disk and the shaft, they will settle at some intermediate radius. So because the disk is compressing from outside, the shaft diameter will shrink down. So this red line shows that the shaft has become smaller than its original radius. So this one is the original radius of the shaft, and the red one is the radius after shrink fitting. And similarly, the disk which was having initial radial distance as shown by the dotted blue line will match with the red line, and that is where the assembly will happen. Now, with respect to the question that we are discussing, let's imagine the situation that you want to separate this assembly. Now, in order to separate this particular assembly, again you will have to heat the disk, so will be, in order to loosen the assembly, we'll have to heat the disk by an amount which must be equal to same delta T what we calculated earlier. So unless you expand the disk by an amount which is equal to delta T, you cannot loosen up the assembly. So when you heat it by this delta T, you will realize the same situation as it was there during the assembly. So the disk will have diameter equal to the um, unexpanded diameter of the shaft, and then you will be able to loosen it. So what, in terms of the displacement, it means that in order to loosen the assembly, whatever is the radial displacement of the disk, it it must be equal to delta. Now here we are considering that the shaft we are keeping at the room temperature, so there is no displacement of the shaft. But imagine that we are hitting both shaft and the disk. So in that case, again, we will have to have meet the same condition. Only thing is, since we are hitting both of them, the radial displacement of the disk must be higher than the radial displacement of the shaft, and the difference between them, that is the relative displacement of the disk, must be, with respect to shaft, must be equal to delta. Then only the disassembly would be possible. So this is the basic condition that we are taking ahead for solving our problem. So we'll proceed with this point as a starting point for this problem. So we'll be considering this as the starting problem. So our equation becomes UR of disk minus UR of shaft must be equal to delta, and in our problem delta is given as 0.075 millimeters. So I will do all these calculations in meter units because we are having the density. In this case, the forces are being calculated based on rho omega square. So if you consider in millimeter, then the density also needs to be converted, and there will be some unit-wise mismatch or error could happen if you are not careful enough. So we'll safely do all calculations in all length in meters, and forces in newtons, and mass in kg. So 0.075 into 10 to power minus 3, so many meters is uh, the condition that we have to satisfy. And also note that this radial displacement we are not measuring at any arbitrary point in this assembly, but we are measuring exactly where the shaft diameter lies. So wherever is the interference at that radius, that is that uh, contact between the shaft and disc, so that radius is what we are considering here. So which means that the r equal to the inside radius. So inside radius in our case is diameter is 150, so it will be equal to 75 millimeters, so that is 0.075 meters. So for both these cases, r will be equal to 0.075 meters. Okay, so let's proceed with this direction. Now let's first take the UR of disk. This would be given as R divided by E multiplied by sigma theta minus nu times sigma r. Now again, note that we are considering a situation where the disk is just about to separate from that of the shaft. So when they are shrink fitted, there is some contact pressure which exists between these two surfaces when they are about to and that will act as a radial stress at that particular interference. Uh, so when we have the shrink fitted assembly, the radial stress does exist at this particular location. But on the point of separation, at the moment where separation is happening, the shaft and the disc, they will lose contact with respect to each other. And at that moment, you will have the radial stress equal to 0. So the sigma r in this particular calculation will be equal to 0 at the moment of separation. So we need not put the expression for sigma r for doing the calculation. So this is another important point that you should take care of. And now we'll substitute the formula for sigma theta. So we'll have r by e in the bracket 3 plus nu by 8 rho omega square in the bracket b square plus a square plus a square b square by r square minus 1 plus 3 nu divided by 3 plus nu multiplied by r square. So that is the first term, sigma theta term, and minus nu times 0. So that is the sigma r term. So this is the condition that we have to satisfy, and this we have to do at r equal to inner radius, which is in this formula a is the inner radius and b is the outer radius. So we are doing calculations at r equal to a. So which means that this will become a divided by capital E in the bracket 3 plus nu by 8 rho omega square b square plus a square plus b square. So here this r equal to a will eliminate this thing, minus 1 plus 3 nu divided by 3 plus nu multiplied by a square. So that is ur of the days. Now we'll substitute the values of the parameters. So a is 0.075 meters, the inner radius of the disk. EV is given as 214 GPa. So that is 214 into 10 to power 9 Newton per meter square. So remember that we are using all consistent units. 3 plus Poisson's ratio is given as 0.3 divided by 8. At present, I will maintaining it as rho omega square as rho omega square. Later on, we'll substitute the values. That is just for the ease of uh, uh, comparing the numbers. Then we have this b square and b square, 2b square. So that is 2 multiplied by the outside radius of the shaft, which is 750 by 2 or 0.375, the whole square, plus a square, so 0.075 the whole square, minus 1 plus 3 into zero point 0.3 divided by 3 plus zero point 0.3 multiplied by 0.075 the whole square. So this will get it as 4.1005 into 10 to power minus 14 rho omega square. Now let's calculate the UR of the shaft. So for this, we have to use the formula which is corresponding to the solid cylinder that we have developed earlier. So UR of shaft would be given in the similar fashion. So here I'm directly using at R equal to A. So that is the diameter of the shaft. So that will be A divided by E in the bracket 3 plus nu divided by 8 into rho omega square b square minus 1 plus 3 nu divided by 8 rho omega square a square. So this we will get as a is 0.075 divided by 214 into 10 to power 9. 3 plus nu is 3.3 divided by 8 multiplied by rho omega square into b square. So that is 0.075 the whole square minus 1.9. So 1 plus 3 nu is 1 plus that is 1.9 divided by 8 into 0.075 the whole square. Okay, here just some notation confusion. So here I use the formula that we have discussed in the classroom. Here it is in terms of B. So notation wise, this is the outside diameter of the shaft. So B is the outside diameter of shaft. And that is where we are doing all the calculations. So here we are considering, so I'm just some notation confusion. So I'm just considering this R equal to OD of shaft, because the formula is given in terms of the radius of the shaft, and we want to calculate deformation at the radius of the shaft, outside radius of the shaft. So sorry, not diameter, outside radius of the shaft. Okay, so now notation wise it is okay. So only in the earlier formula we have used the notation A, which is the inner diameter of the disc. If you refer to the shaft formula, that is written in terms of the B, which is the outside diameter of the shaft, outside radius of the shaft. So just corrected that notation. So here we get this answer as 3.45 into 10 to power minus 16 rho omega square. So for the disk, we had got this as the displacement, and this is for the shaft. Now we'll use our main relationship, that UR of disk minus UR of shaft must be equal to the radial interference. So therefore we are having 4.1005 into 10 to power minus 14 multiplied by rho omega square minus 3.45 into 10 to power minus 16 into rho omega square equal to 0.075 into 10 to power minus 3, and here we'll substitute rho equal to 7850 kg per meter cube, which is given in the problem. And if you solve for omega, you will get the value of omega as 484.7 radians per second. So if you multiply this by 60 by 2 pi, you will get the answer in RPM. So the RPM is 4629 RPM. So this is the answer. So when you start rotating this assembly at 4629 RPM, you will find that the disc will get separated from the shaft after overcoming the radial interference which was given for this case. The second part of the problem, it asks for what is the maximum circumferential stress in the disc at this RPM. As we had seen in the classroom session, the expression for maximum stress in the disc, it happens at the innermost point of the disc. So maximum stress in the disc at this RPM would be given as sigma theta max which is 3 plus nu divided by 4 rho omega square b square plus 1 minus nu by 3 plus nu a square, and it happens at r equal to a. So here a is the inner radius of disk. So that is where we are looking for this particular case. So if you substitute the numbers, it is 3 plus zero point 0.3 divided by 4 into rho is 7850. Omega we have calculated as 484.7, the whole square. This multiplied by b square, which is 0.375 square, plus 1 minus nu divided by 3 plus nu multiplied by 0.075, the whole square. So this turns out to be 215.8 into 10 to power 6 Newton per meter square, which is nothing but 215.8 megapascal. So this is the answer to the second part of this question.